Our final speaker this morning is going to be Dr. Lynn Loomis, Adjunct Professor, Natural Resource Management, Sul Ross State University here in Alpine. Lynn Loomis was born in Oklahoma and grew up riding horses and driving tractors on the family farm. His parents, Delbert and Joanne Loomis, worked hard and saved in order to send their children to college. To learn how to see things, Lynn took college courses in geology, botany, soil science, and range ecology. In 1989, he began learning the field craft of soil science. He made soil maps for the USDA on the gently dipping limestone strata of the Edwards Plateau. Then 4 years later, Lynn enrolled in the block faulted terraces of the Trans-Pecos. The real learning took place in the field at the feet of the Solitario, Santa Elena limestone, horst and graben tectonic structures. It gets better. Gravel pediments, zeolites, gyp Gramma, leather stem, and banded vegetation patterns. He had the opportunity to study some of God's best work. And Dr. Loomis is with us virtually, so we're going to turn it over to him now.
We see what we look for, and we see what we're trained to see. If you want to learn plants, hang out with folks who know plants. I learned plants from Clay Lindley at Marfa back in early 1990s. The great American philosopher of science, Yogi Berra, said, you can see a lot by just looking. There was a lot to see in West Texas. The trick is learning to read what you see. This is a landscape down on the Rio Grande, Black Gap Wildlife Management Area. The landscape appears chaotic, but underlying order exists in the landscape. Order between the vegetation, soils, and the environment that they exist in. Soil scientists, range ecologists work out those predictive relationships, and they can predict the vegetation potential that's unseen. They can predict the soil morphology below ground and invisible based on visible surface features that they can see. Those environmental factors grouped under 5 headings: parent material, relief, time, climate, organisms. Those 5 factors control the ecologic processes and pedologic processes that result in the vegetation and soils that exist on the landscape. We'll focus on this 5-factor relationship. We'll look here at the seeing the landscapes in Texas Big Bend. And we're here, y'all are there in Alpine. I'm a friend's home in Weimar. So we have El Paso County, Hudspeth County, Culberson County. We won't think about those too much today. And we got Reeves, Pecos, and Terrell counties. Won't talk about this too much. We will talk about Jeff Davis, Presidio, and Brewster counties, which are the Big Bend counties. These counties have weird shapes in Texas. Most counties are kind of square, but out here, my head is still in West Texas, y'all. The counties have a different kind of shapes. This is a Landsat scene captured about 20 years ago. You can see the mountainous terrains. Here's the Apache Mountains, the Davis Mountains, Bofocios, some more Davis Mountains in Brewster County. See the dry basin areas along the Pecos River, fairly reflective. A lot of albedo there. So this is the relationship I'm talking about. We have a couple of things on the left-hand side of the equal sign, soil and vegetation. These are the dependent variables, the things that develop as a result of the independent variables. These are functions, the F, and talking about relationships here, of 5 interacting factors. And the order of these is not important, and they change, and they will change in this presentation. We have climate and organisms. Climate, the thing you think about. So the summer monsoon in West Texas, temperature, Evapotranspiration, wind is a really important factor, fire, the monsoon. Organisms, we have about 2,500 species in West Texas. We're talking about the ecological amplitudes, the environmental tolerances that these plants have, and the interactions between them, competition, mutualism, homogeneism, and even bioturbation. The organisms stir the soil. We have parent material and relief. Parent material, we're talking about limestone, igneous calderas, conglomerates, zeolite, smectite clay, and the faults that really put odd things close to each other. Relief, that's the ups and downs of the landscape. Slope gradient, aspect, how high is the area above the stream channel? Wetness index, caldera drainage. And when time is the fourth dimension of the physical universe, talking about disturbance, how long has it been since the disturbance took place? Talking about climate change. Herbicide application could be here in time, and livestock grazing could be included in this factor of time. It's a pretty simple model. There's a 7, I guess 8 letters if you count the function. You can count all these things on 2 hands, and you can think about 5 things, these 5 factors, almost simultaneously. It's an expansive model. Well, so climate organisms are the active factors. They make things change. They transform the initial parent material and relief into the soils and vegetation see on the landscape today. And then time is the 4th dimension of the physical universe. This relationship, published by a Russian soil scientist, and this is a quote from him: "If the factors in 2 areas are similar, the soil should be alike too," he wrote. The strength of this is, if we can study the factors, we study the parent material, relief, time, climate, and organisms, we are able to predict what the soil should be like. And that's the power of this relationship. And he published this in 1886. We've been using this model for 135 years, and so far we haven't found anything as simple that's better than this. This model was made popular in the United States by Hans Jenny in his book Factors of Soil Formation in 1941. His student Jack Major at UC Berkeley published a paper on the functional factorial approach to plant ecology. This has been used by soil scientists since the early 1900s. Berman Hudson, in a paper 1992, said that this relationship, these 5 factors, are the paradigm of soil survey. This relationship is the general solution to the particular problems that range ecologists and soil scientists face today. Of these 5 factors, we can see parent material, relief, and organisms in the field or on air photographs or satellite images. And that is the evidence used to predict what kind of vegetation potential, what kind of soil might exist on an area. And with the advent of GIS in the field, we can take the prism grids produced by the Oregon Climate Survey and have continuous information about the temperature, mean annual temperature, precipitation, and calculate water balance for an area. And these are all powerful tools to make predictions about the habitats for the plants that live out there. So dive into these factors. Climate is just a summary of weather observations. I was weather observer at Marfa for 5 years and recorded rainfall and temperature and snow when it fell. And someone has summarized that data. We talk about the water supply, the landscape, rainfall, snow, relative humidity, dew point. It might rain in West Texas when the dew point's above 50 degrees Fahrenheit. Below 50, not much chance. Energy, lots of solar energy in West Texas. Evapotranspiration is a function of the temperature and the wind, the amount of water loss. We'll talk about that some later. Wind is important, the dust it brings in, and fire. It's been about 10 years since the big fires in West Texas, the really big ones, but we've had some small ones just about every year. So a couple of rules of thumb about climate in West Texas. As far as temperature, or no, I'm sorry, rainfall. Rainfall increases about 1 inch for every 50 miles. You get closer to the Gulf of Mexico, the source of atmospheric moisture that feeds the summer monsoon in West Texas. And that 50 miles, pretty relaxed gradient, and exists across a lot of Texas. In West Texas, what really makes things interesting is the lapse rates with elevation. About 2.5 inches more rainfall, increase in rainfall for every 1,000 feet you climb in elevation. So any of y'all been to the top of Elephant Mountain? 6,200 feet elevation, the base of it at 4,200 feet. So you have 5 inches more rainfall at the top of the mountain than the bottom. And you look at the vegetation and the physiognomy, and it shows. Another rule of thumb, mean annual air temperature decreases about 1 degree for every 50 miles you go north, closer to the polar region. Marfa is about 60 miles north of Presidio, be a degree cooler than Presidio by this relationship. But what takes charge in West Texas is the big changes in elevation, about 2.5 degrees Fahrenheit cooling for every 1,000 feet of elevation that increases. So Marfa at 4,700 feet, Presidio 2,600 feet. Marfa should be 5 degrees cooler because of elevation. You add that 5 degrees to the 1 degree for the 15 miles north, and 6 degrees of difference by the calculation, and it's usually closer to about 10 degree difference. So we can take the GIS grids, the PRISM grids, take the grid for mean annual precipitation, subtract from it the grid for mean annual potential evapotranspiration, and come up with this grid we see on screen here, annual water balance. It's rainfall minus precipitation. And in West Texas, PET, the evapotranspiration, is almost always greater than precipitation. It doesn't matter how much. There's about 2 square kilometers in the top of Mount Livermore where there is as much precip as evapotranspiration, and that's where you find the quaking aspens. As you decrease in elevation, it gets progressively drier and drier till down at Presidio, the water balance is 1,100 millimeters below zero, 1,100 millimeters, more than a meter more than of evapotranspiration than there is of rainfall. Plants down here on the Rio have to deal with water stress most of the time. We have these really strong environmental gradients. Annual water balance is the one best predictor of vegetation physiognomy that I found. Precipitation is related, of course, PET, of course, but you take the difference between those, annual water balance, and that's the best predictor I found to predict vegetation physiognomy. Now you get up in the top of the Sacramentos, there's a probably 8-inch water surplus. As you proceed lower down, we have an increasing water deficit. Maps like this are really useful in making a guess as what will the conditions be on a ranch that I haven't visited before. Really useful tool. Now, underlying all this is the overlying principle of range ecology. The living source for plant growth anywhere in West Texas is water. What's the water supply? When is it coming? How long does it last? So the vegetative zones in the Big Bend, I'm focusing here in the 3-county area, are based on classes of this annual water deficit. There are mappable ranges of annual water deficit, and I've just delineated these vegetative zones. There's a couple in here that are additions to the standard ones that have been in the minds of range ecologists, West Texas soil scientists for 60 years or so. You get in the high mountains, you have the mountain woodland, even some forests up there, more than 60% tree cover, but usually it's more open than that. There's a ring around the woodland that's a savanna. Grasses and trees share a codominance, the high Davis, not the high Davis mountains, but kind of the higher foothills, you might say. We have the mixed prairie, mainly short grasses with some mid and tall grasses mixed in. They dominate. The shrubs are in this environment subdominant usually. Preceding lower elevations, we have the desert grassland. This is a shrub savanna, where grasses and shrubs share codominance in the higher successional status areas. If you put a lot of livestock on a desert grassland area, cattle can decrease the grasses, but you take the cows out and the grasses will respond. They'll return. That lighter colored brown at the lowest elevation is a hot desert shrub, emphasis on hot. I tried not to go to that kind of country between March and October. I tried to avoid that country. You go down there in the wintertime, where it's shrub dominated. This physiognomic type has some grass, but you have to look for it. And then down along the river, have the very hot desert shrub, not very extensive. And it's a new concept I've been trying to develop and understand the effect of drier temperatures, drier climate, hotter temperatures on the plants that grow there. There's some unique plants that grow right down on the river. So we'll talk about these in order. Now, I've talked about annual water balance as opposed to precipitation. And precipitation is what most people think about, they talk about, but I'll show you why I've migrated to annual water balance in my thinking. This is a bar chart showing precipitation in blue and evapotranspiration in yellow for the mountain savanna, mixed prairie, desert grass, and hot desert shrub zones. And you can see precip is about 20 inches or so, the mountain savanna, drops to 15 mixed prairie, say 12, 14 desert grass and hot desert shrub, 12 have a decreasing precip as elevation goes down. The evapotranspiration, 30 inches, mountain savanna, 32 mixed prairie, almost 40 desert grassland, approaching 50 inches in the hot desert shrub zone. The rainfall in mountain savanna meets about 3/4 of the water demand. So plants up there are pretty happy most of the time, and you get big plants. Mixed prairie, about half the evapotranspiration is met by rainfall. Desert grass in 1/3, hot desert shrub about 1/4. Look at the deficit numbers, the difference between PET and precip. So these are the annual water deficit, 8 inches mountain savanna, say more than that mixed prairie. It doubles that in the desert grassland, and it jumps way up the deficit in the hot desert shrub zone. We have a relationship between precip and elevation. It's a direct relationship. The PET minus precip, the water deficit, increases as you go down that country. And the effect, the slope of the line for this water deficit is about twice the slope of the line for precip. If you're thinking only in terms of precipitation, you're ignoring 2/3 of the water balance equation. So we, in the Marfa Soil Survey Office, when I worked there, we adopted annual water deficit, annual water balance as the key for understanding plant-soil relationships in West Texas. So Rex Dobbelmeyer wrote in his book that plant communities, which is V in this equation, are a result of two phenomena: the ecological amplitudes of the plant species as they interact with the variable environment, which are the other four factors: climate, time, paramaterial, and relief. We'll change our attention from climate now to organisms. Talk about the ecological amplitudes of 2,500 species. And we'll say that all Gramma grasses were not created equal. In my work at Marfa Soil Survey Office, we collected veg plot data on 12 or 15,000 veg plots, made a species list, and assigned each species to a cover class. So I have here the ecological tolerances of five Gramma grasses. Here we have the state grass of Texas, Cytops Gramma. Cytops Gramma was observed in about 500 veg plots between 500 and 600 millimeter water deficit, which is desert grassland. These colors on the chart here relate to the annual water deficit, and the annual water deficit classes relate to these vegetation physiognomic classes, these veg zones. So Cytops Gramma tolerates conditions from pretty moist out to pretty dry. Cytops Gramma really doesn't tell you much about the habitat it grows in. Very wide ecological tolerances. The highest abundance is in the desert grassland, and it drops off slowly as you get wetter precip, but it drops off pretty fast going drier. Blue Gramma, kind of the grass we think of in the mixed prairie zone, dominant grass. Again, we have annual water deficit across the bottom, and we have Blue Gramma maxed out in the mixed prairie. It climbs up into the mountain savanna some, but it drops off pretty quickly. We don't normally think of Blue Gramma as a dominant in the desert grassland. I attribute this abundance here to Blue Gramma that we observed in water receiving landforms in the desert grassland. It's normally not that abundant, and it drops off real fast in the low end desert grassland, the shrub savanna country. This is Harold Gramma. Y'all might have been more formally introduced, and we call him Harry now. Harry Gramma is a less abundant than Blue Gramma, but the ecological tolerances, the amplitude of conditions it tolerates is about this like Blue Gramma. And we have this Gramma species with hairy and smooth segments of these stems. That's Black Gramma. Black Gramma is the most abundant Gramma that we observed in West Texas, of these 12 or 15,000 veg plots. It maxes out in desert grassland. It's pretty abundant in mixed prairie, but it drops off. We think of desert Black Gramma as the dominant grass in the desert grassland, that 500 to 700 millimeter water deficit country. And not much in the hot desert shrub country at all. In the hot desert shrub, you see this grass, Chino Gramma, Budula ramosa. And here it's absent virtually in these wetter zones. We have pretty high abundance, 200 observations of Chino Gramma in the two segments of the desert grassland. But we normally think of Chino as the dominant in the hot desert shrub. I'm guessing these values here in the desert grassland climate zone are sites where it has a pretty strong south aspect, and the solar radiation results in a drier soil climate that's drier than the atmospheric climate. So all Grammas were not created equal. When you're talking about we talk about climate and organisms, that was we'll keep on here talking about climate. We have these climal sequences. We have the 5 factors. We're going to hold 4 factors similar. We'll hold parent material similar, release similar, time similar, organism similar, and vary climate. We have these different colored columns for the veg zones. And we have a sequence of vegetation on different climates within the igneous substrates. And we'll name these for the soil series that dominates there. High Davis zones, we have the Madrone soil series on igneous bedrock. The mixed prairie country, it's the Brewster soil series on igneous desert grass, and it's the lava soil series. And the hot desert shrub, it's the Studi Butte soil series. And we'll look at examples of what the vegetation looks like on igneous substrate in these 4 climate zones. We can also look at climate sequences on limestone and alluvium, but we'll not do that for sake of time. So mountain savanna country, we're talking 6,000 feet up to the top of the world, the top of Livermore. Water balance 0 to 8 inches of deficit. It's the wettest habitat in far west Texas. In the vegetation, you'll see some oaks, gray oak, emery oak, pines, ponderosa pine, or something like it, maybe Arizona white pine. There's depending on where you are, different species of pinyon, and then alligator juniper. Shrubs, you talk about mountain mahogany earlier today. You'll see a lot of silverleaf oak in the drains. Grasses, they have little blue stem, that kind of country. Pinyon rice grass, Indian grass, and Cytos Gramma. Taller grasses in the mountain savanna country. Wetter environment, pretty good water supply. Here's a landscape shot from Bridge Gap there on the Davis Mountain Preserve, looking toward the southeast. You see these tall ponderosa or Arizona white pines. Since then, this picture was taken probably about 2002. We've had some outbreaks of pine bark beetles and fires. These pines here are burned, but there's a regeneration of these pines now. The last time I was up there. But you see the amount of woody cover on this south aspect. We're standing on a north aspect and pretty good tree cover there. But over here on the south aspect, more pinyon and juniper. We drop down to the mixed prairie. This is the zone Marfa, Alpine, Fort Davis, 4,500 to 6,000 feet elevation. The water deficit, 8 to 20 inches. Again, the precip meets about half the water demands. Vegetation, we have some trees on the shallow soils to igneous bedrock, emery oak, roast-rooted juniper. On the deeper soils, you have sotol, western honey mesquite, a little different brand of mesquite than is on east of the Pecos River. Western honey mesquite, paired thorns, more leaflets, smaller leaflets on the leaf than the regular honey mesquite east of the Pecos River, and javelina bush. Grass is the blue Gramma dominant grass. We have some black Gramma side oats. Cane blue stem on the little concave landforms where water can penetrate more deeply. Springle top and Tobosa in the swales. Here's a shot, Paisano Pass between Marfa and Alpine. You see a pretty good cover of trees, junipers and oaks. This is the Brewster soil, but a really good continuous turf of grass in the understory. And this would be blue Gramma, side oats, things like that, some black Gramma. This is the igneous hill and mountain ecological site in the mixed prairie vegetative zone. We'll drop down and the desert grassland. This is your Valentine, Shafter, Marathon kind of country, 3,500 to 4,500 feet elevation. The increasing water deficit, 20 to 28 inches. The precip meets about a third of the evapotranspiration demand. We're talking about different woody plants. We have creosote bush dominating western honey mesquite, not necessarily together, but sometimes. Creosote and mariola, they live together a lot of times. Sotol and elbow bush. Grass is, that's where your black Gramma and Tobosa kind of dominate. Side oats Gramma again. We've had side oats in the mountain savanna and mixed prairie desert grassland. Side oats doesn't tell you much about the habitat. And here's a shot. This is down at Big Bend Ranch State Park. One of the members of the Texas State Longhorn herd that resides down there on the lava soil shallow to igneous bedrock, less than 20 inches to root limiting layer. We have grasses and shrubs share co-dominance here. Probably viscid acacia. You see some ocotillo in the background, but a pretty good cover of grass there. This looks like some kind of a 3-on, but there's also some side oats Gramma and other mid grasses, but there's some gaps in that grass cover. Dropping down one more zone into the hot desert shrub zone, emphasis on hot. From river level, Rio Grande level up to about 3,500 feet elevation. Your water deficit goes from 28 to 45 inches. The plants undergo water stress almost all the time. This is the country that's ephemeral range. If you're really going to graze it wisely, you wait for rain, you put the cows out, when it stops raining, and the cows eat maybe a quarter of the grass, you take them out. It's that kind of country. Vegetation down there, woody plants, that's where ocotillo. Liz, you can find ocotillo in the mixed prairie and desert grassland, but they'll be on very thin soils. You can see ocotillo. They're a Paisano pass between Marfa and Alpine on a steep south-facing slope that's very shallow to igneous bedrock. Creosote bush, and you lechuguilla becomes dominant. Candelia on your mainly limestone substrates. There is sometimes Candelia on igneous. Now, leather stem, Heteropha dioica, is one of the indicators for this hot desert shrub zone. We call plants that can live down here and can tolerate the heat and can't tolerate the cold, call them hyperthermophiles. Grasses down there, that's where your Chino Gramma comes in. False Gramma, Cathysticum erectum, bush mealy and fluff grass are down that hot desert shrub country. Here's a photograph taken by a student, Dan Hinkline. He did his thesis work at Big Bend Ranch State Park. He looked at the vegetation plant communities, the associations and alliances, shallow soil to igneous bedrock, the Studi Butte soil, lots of exposed rock, some big fragments, not much fine earth there on the surface. Chino Gramma, real fluffy grass. You have blind prickly pear, some Engelmann's prickly pear, and ocotillo. Pretty tough environment to be a plant, except maybe in August after a rain, but those plants are dormant most of the year. So here's another climate sequence on a loom. We'll look at briefly how the climate, how the water balance affects vegetation across West Texas. Up there at Mount Locke, near the observatory, you have the mountain savanna, deep soil forming alluvium. You have a continuous turf of blue Gramma here. Hardly any bare soil exposed. And in the background, lots of alligator junipers. Water deficit up there is on the order of 0 to 8 inches. Drop down the mixed prairie. This is on the Mims Ranch north of Marfa. Again, a grass dominated system, but you can see some gaps in the grass cover, some bare soil. Wider diversity of species here. You got Cytos Gramma, blue Gramma, cane blue stem, green sprangletop, 2 or 3 different low muleys. Fairly diverse in grasses here in the mixed prairie zone. Drop down to the desert grassland. This is south of Alpine, about 30 miles. Working with a student, Chris Jackson, who is studying Platylemma species, one of his study sites. So we have grasses and shrubs, Characoidomus here, western honey mesquite, some tarbush in the background. You have some burrow grass associated with this shrub, but you have a lot of bare soil in the desert grassland. The precip meets about 1/3 of the evapotranspiration demands there. And then drop down to the hot desert shrub, emphasis on hot. We have some tobosa grass that probably grew 2 years ago. This year, not enough rain to wake it up. See quite a bit of shrub cover in the background. Another climate sequence on alluvial soils, deep alluvial soils. We have a increasing elevation going from the Big Bend National Park. This is north of the Rosios, a few miles up to Livermore area. We have increasing water depths as we go down the hill. So climate matters regionally. The effect of climate is a regional difference. It's not a short space distance. So we have this spatial hierarchy of factors controlling vegetation. We talk about the annual water balance. Well, now we'll focus on the geology and landforms, the things that occur on short distance. Geology map of Trans-Pecos, Texas. It's just a mixed up mess. You got time. It's a wonderful puzzle to solve. If you're in a hurry, forget it. A lot of different kind of rocks, different ages. All the different geologic ages are represented here in the Trans-Pecos. We'll talk about briefly the history. We have Precambrian, Paleozoic, Mesozoic, and Cenozoic. The Mesozoic and Cenozoic are the Paleozoic and Mesozoic are metasedimentary. And then what makes West Texas different is the Cenozoic rocks. So south of Marathon, you have the Caballos novaculite, results in the Chert Hill ecological site with a unique assemblage of plant species on that substrate. The Testness shale, they're in the Solitario, they're around Marathon habitat. We have the Santa Elena limestone, a lot of that South Brewster County, South Presidio County. This is on Black Gap Wildlife Management Area. You see this rock topple that took place there in time past. We got the Penn clay. They're in Studi Butte. This substrate was to make a really thin soil. And that soil supports plants when it has a veneer of gravel on it. Where that veneer has been stripped off, it really doesn't support plants. So the thing that makes West Texas unique, different from the rest of the state, is Cenozoic volcanism. And again, we're here in Alpine. This is taken from work by Chris Henry and Fred McDowell 35 years ago. They documented the occurrence of about 20 volcanic calderas in West Texas, from Sierra Blanca down to Big Bend National Park. About 20 calderas in about 20 million years. Very dusty time, a lot of volcanic ash. And this is a map of the tertiary rocks, West Texas. As a former resident of Presidio County, I'm glad to say that Presidio County hosts more igneous rocks than Jeff Davis or Brewster County. These authors, Mason, Pyle, and Oppenheimer, published a paper 20 years ago about the most extensive explosive volcanic eruptions in Earth history. As expected, find Yellowstone on there twice. The eruption number 2 on the list, number 22 on that list. You see the igneous rocks of that age in the western US. We have some members on that list in West Texas. They're here in Alpine. Chinati supervolcano is number 21 on that list of most violent volcanic eruptions in Earth history. Presidio County. And then the Paradise Mountain supervolcano, they're just west of Fort Davis, has 2 eruptions on the list, number 27 and 28. All the mountain peaks you see at Marfa and Fort Davis are igneous in origin. There are parts of the Alpine, you might be able to look east and see the glass mountains, which are sedimentary rocks. But otherwise, Alpine mountains are all igneous in origin, volcanic, and then there's intrusive rocks too. So this is a kind of thing that happened in West Texas a number of times. A pyroclastic flow. This is a photograph taken with the eruption of Mount Pinatubo 30 years ago in the Philippines. We know that the camera survived this pyroclastic flow. We don't know anything about the photographer or the vehicle back there. But this kind of thing happened time and time again with the eruption of the calderas in West Texas. So we'll focus on the eruption of Chinati volcano. We're here at Alpine. You see has the location of Chinati Mountains. That's where the existing caldera is now. Caldera is a violent eruption, evacuates the lava chamber, and the overlying rocks collapse into it. You can actually drive into this caldera on the Cibolo Creek Ranch. Just ask them to take you on the 3-hour tour, and you can get in the heart of that caldera and see some of the internal structure. That's what's left of that volcano now. The eruption blasted out for a distance of about 60 miles from Valentine down to Terlingua, Alpine, over to the Sierra Grande anticline arch west of the Rio Grande, was covered with volcanic ash from the pyroclastic flows of Chinati supervolcano eruption. Every living thing in this terrain was killed when the eruption took place, about 30 million years ago. Now, this is a shot taken from about 15 miles south of Paisano Pass. We're looking southwest on the skyline down there. You see Chinati Peak. We have about 1,000 feet of volcanic ash exposed on this scarp. That's probably volcanic ash from the Paradise Mountain caldera, or maybe Paisano Peak caldera. And then the big one happened, the Chinati supervolcano erupted. There's the peak, the remnant, erosional remnant of the volcano that erupted that Mitchell Mesa ignimbrite 30 million years ago. That's the source. Here in the foreground, this cap rock is the Mitchell Mesa ignimbrite. We're standing on here, there's some here, and in the background, that's capped with Mitchell Mesa ignimbrite. The ash cloud was so large, it extended out a distance of 40 miles, and it accumulated to a depth of about 40 feet, and it was so hot it fused to make this rock that holds up this 1,000-foot high scarp. Very violent volcanic eruption, the Earth history-changing eruption. After the volcanism, we had the basin and range faulting. The North American plate stretched. To accommodate that stretching, we had these graben blocks drop down in relation to the horse blocks. So you see this horse and graben structure all over West Texas. This shaded relief map of the U.S. shows the basin and range topography here, Nevada, Utah, Arizona. It continues into West Texas. Here's the source, this shaded relief map. Zooming into the southwest, you have the Rio Grande Rift, basin and range, continental stretching with the graben blocks dropping down to accommodate that stretching. And then here West Texas, we have the 200-mile rift going from the Sacramentos down to about Marfa, and then continuing down to the Chisos. You have the Presidio Bolson, which is a tectonic basin filled with sediment eroded from the Chinades and Sierra Vieja. John Udden wrote this in 1907. When you look at the Chisos country, you all got to remember that between 2,000 and 10,000 of material has been eroded from that landscape. A lot of erosion taking place, and I'll say that the forces that remove that sediment from the landscape are still active. They're just waiting for soil to be left bare and exposed, and the erosion will strip what soil we have left here out, just like it did these 2,000 to 10,000 feet of sediment. Had stupendous geologic erosion in West Texas. I'm standing here on the summit of Elephant Mountain looking south. Elephant Mountain is about 6,200 feet elevation at the top. Looking south, there's Santiago Peak, 6,500 feet, about 12 miles south. 25 miles, so you have the 9-Point Mesa, not quite as high, 5,500 feet. And on the distant skyline, you have the Chisos summit out about 6,900 feet. These are all capped with intrusive igneous rocks. That's magma that came up from below, and it spread out to make a sill, a horizontally elongated body between sedimentary rocks. And it had a mantle of roof rock on top that slowed the cooling and resulted in the formation of visible crystals. So have a sill on top of these three mountain masses that formed underneath a layer of roof rock. We don't know how thick it was. And we expose this area to millions of years of erosion. And at Elephant Mountain, there's been about 2,800 feet elevation, about half a mile of erosion. Santiago, about the same amount. 9-Point Mesa, 2,000 feet of erosion. And down to the Chisos, another half a mile of erosion. It's taken place since the emplacement of the sill that now is at the top of these mountains. Tremendous volumes of material eroded out of this landscape. The material carried by the Rio Grande or some precursor and partially filled the Gulf of Mexico basin. Now, the erosion wasn't a buzz saw. It didn't plane things off even. It resulted in a bunch of different kind of landforms. This is a screenshot out of Peterson's Basin Range landforms. We have a couple of horse blocks that thrown up with a gravel block in between. And the erosion has sculpted a rich variety of landforms in here. And these landforms provide the stages on which plant succession and soil development take place. And if you can learn to read these landforms, you can infer a lot of history and a lot of the properties of soil and vegetation that occur on them. One more thing about the factor of relief, the flow path patterns can dictate water balance and the amount of water that plants have available to them. This is south of Alpine. We have a basalt capped mesa with different shapes of landforms on the side slope. Here on the left, we have parallel flow paths. So as you proceed down slope, you get more and more water from upsource available, but these paths are parallel. Here to the right, we have the divergent flow paths. Water is spreading out. So the area here is drier here than it is over there because there's less water running at it. That water is diverging. Compare that to the convergent flow paths in this head slope where the water is gathering together. So the plants down here have access to water from this big amphitheater. So the landforms really affect the amount of water that plants have available to them, especially in these steeper terrains with parallel, convergent, and divergent flow paths. And aspect, we've seen how aspect works in the high country. We normally don't think of aspect working down along the Rio Grande. This is in the national park. The Rio Grande is back here about a half a mile. We have Chino Gramma here growing on a cool north aspect. Not much on the hot south aspect. So we have this landscape we saw earlier. As a soil scientist, I went down and drew out the different soils and the different ecological sites that occur in this landscape and take this chaos and try to make some sense of it. So we have the Rio Grande corridor with all the rhododendrons and other things. There's also in here some black brush acacia. We saw black brush acacia that had been gnawed off by a beaver. Pretty cool. That's the Loamy Bottomland ecological site. Adjacent to the river on a terrace that has a gravel substrate, a little less run on water, less water supply. Deep and shallow soils that are kind of mixed in together. We have the gravelly ecological site. This is in that hot desert shrub country down along the Rio Grande. And then we have the uplands where I have limestone bedrock within 20 inches of the soil surface, and a different suite of plants occur here. Now, the Rio Grande is the international border, but that doesn't stop the ecological sites from continuing south into Mexico. So there is a document describing plant succession, state and transition models for the ecological site here in the US. The ranchers in Mexico can take that, read that, and the information would apply there as well. So for short-term differences in vegetation and soil, likely the reason is geology and landform. Okay, so here's our paradigm, the 5 factors that control soil and vegetation, climate organisms, the active factors, permaterial relief, the passive factors, and time, which could include disturbance and succession, herbicide, and grazing. These factors dictate what soil and vegetation are. If we learn to read those, then we can make predictions. Talk in terms of climate, if your differences take place across large distances, 10 miles, 20 miles, you're probably talking about a climatic difference. We've seen the impact that climate has on vegetation on deep soils forming in alluvium. We looked at differences that occur, short scale differences, an order of 10 feet or 20 feet or maybe half a mile. Those differences are because of geology and landform, resulting differences in soil and vegetation potential. With that, I'll wrap up. I work for Alameda Foundation. The motto of Alameda Foundation is cultivating growth. We want to enhance the development of young people, give them opportunities, young people in the Big Bend, and also another priority is to restore the Alameda Creek Valley to conditions that might have existed before Anglo-Europeans settled in the 1800s. My contact information, I'd be glad to correspond with y'all, send a text, send an email. I'll be glad to answer any questions. And I think my time's up. Appreciate y'all's attention today.
Dr. Loomis, nod your head if you can hear me.
I hear you.
Okay. I enjoyed your talk. I'm repeating this again. I enjoyed your talk. It reminds me of being in school eons ago. And I think some synapses in my brain are starting to reconnect. There's a concept that I can't wrap my head around, and that's in all these ecoregions you were talking about, every one of them has an annual water deficit. And if I look at my body and I always had an annual water deficit, I would not be alive. How are these plants in all these regions living when they're always living with an annual water deficit?
Plants have a number of adaptations to deal with water stress. Some of them avoid the stress, either because they exist as seeds, the annual grasses, the 6 weeks Gramma, needle Gramma. They don't even try to grow when it's dry. They avoid the drought. Other plants tolerate the drought. Creosote bush, leaves, stomates can close up, and they conserve the water that the roots are able to extract from the soil. Plants adapt to the dryness by their photosynthetic pathways. Plants capture carbon dioxide from atmosphere in different ways. And some of those ways allow them to open their stomates at night when the water loss potential is a lot less, taking in the carbon dioxide and then close up their stomates. And then in the daytime, they capture that carbon dioxide into carbohydrates. Plants access deeper reserves of soil moisture. There was an excavation by my home in Marfa a few years ago, 20 feet deep. And the crew brought up some soil that had been down there, and that soil was moist. This is in 2011 when it was really, really dry, and the mesquites were still green and growing some. The grass is very dormant, but mesquite had its roots extending down into that deeper zone where there was a little bit of moisture. Not a lot, but it was enough to keep them alive and keep them growing. So plants have a number of different adaptations they can deal with drought stress.
I'm curious about a location near Alpine. We don't get to West Texas very often. Is there a place that we could go visit that would be high mountain and cool temperature? That would be simple driving distance from Alpine. You mentioned some mountains, but when I Googled them, they're like 300 miles away.
So a mountain that is very accessible from Alpine is Sul Ross Hill. Just drive up to the Sul Ross campus. There's a number of kind of high-end dormitories on the edge of the mountain. Just drive up the mountain, park in the parking lot, and hike up there, and you can get on the mixed prairie Ignis Hill Mountain Ecological Site in Alpine, right there edge of town.
What time would that be? I didn't understand. Or could you spell what this mountain name is?
Sul Ross Hill.
Oh, Sul Ross.
Yes, sir.
All right, give everyone, give Dr. Loomis a hand, everyone. Thank you very much, sir.
Yes, sir.
Thank you for your presentation.